session is the first one in the spring term. And today we have John van de Wetering, and he's going to tell us about optimizing T-count is NP hard, but optimizing parameterized circuit is sometimes easy. And this is based on 2 papers. And the floor is yours.
All right, thanks, Sarah. Yeah, we figured it would be weird if I both chair this session and give the talk, so I'll let Sarah do the honors. Yeah, so this is a presentation sort of combines results from 2 papers. The first with Matthew Amy, and the second with Richie Young, Thomas Laconen, and Alex Kissinger. This is a ZX seminar, so I promise there will be ZX diagrams, but it will take a while before we get there. I'm building up towards using ZX to prove certain interesting things. That's I think, solve an open question that I've been thinking about for at least 7 years. Okay, so first motivation for the first part of the talk, T-count. So the idea is that if you want to do fault-tolerant quantum computing, you are going to need some discrete gate sets, because you can't do a continuous set of gates fault-tolerantly. And a popular choice of this gate set is the Clifford plus T gate set, where the T gate is just a phase gate with an angle of 504. Now, in many architectures from fault-tolerant quantum computing, the Clifford gates are all cheap. The T gate is expensive. That's because it's implemented using different techniques than the Cliffords, and that make it more expensive to do so. And that means that if you want to optimize the cost of running a fault-tolerant quantum computation, then you should be optimizing the T-count, because that is your most important metric of how expensive it will be to run this computation. There are other considerations, but for this talk, I'm just going to ignore those. So T-count optimization, how do we do that? Well, there's a couple of different levels of difficulty that are increasingly more complicated. So at the first level, you can set a trivial rewrites, which is you just commute gates and then combine them. So for instance, 2 T gates together next to each other, they combine to become an S gate. And an S gate is Clifford, so then it's free. Or if you have T and T there, it becomes identity, so they combine. Slightly better is if you realize that if you have a C0 plus T circuit, that you can actually push these C0s all the way to the right, and then you get a whole bunch of phase gadgets. In ZX calculus, you would get phase gadgets, which actually corresponds to a phase polynomial circuit. And then if you have 2 phases that are acting on the same parity of qubits, then those phases combine together. And this also allows you to combine T gates into Clifford gates. The best known way is you can realize that some of these non-trivial looking phase polynomials actually implement trivial phases and then can be cancelled. Yeah, how this happens is a bit complicated, but I'll say a little bit about what these problems look like. But this is sort of the best way we know now to non-trivially optimize the T-count of large circuits. You can also do brute force search for very small ones, but if you want to go to any kinds of size, this is the best thing you know how to do. And that's based on the following observation. So the following problems are equivalent. So determining the optimal T-count of an n-qubit phase polynomial restricted to the C0 plus T gate set. This is what I just described. So we have some phase polynomial, and we are trying to optimize the T-count implementing this thing. Nearest neighbor decoding of an n-bit degree n-4 punctured read-mother code. So this sounds quite complicated, but that means that we have this classical code, the read-mother code, and decoding this code optimally actually corresponds to optimizing T-count, which is quite surprising at first. And then there's a third problem, which is finding a symmetric rank of a binary symmetric tree tensor, a square tree tensor. So these problems turn out to be equivalent, which is very surprising. And it helps us find ways to optimize T-count. But the amount it helps us is bounded, because, for instance, problem 3 here is believed to be NP-hard, although there's no proof of it. There's related problems that are NP-hard, so we believe this thing is also NP-hard. And hence, optimization of diagonal Clifford plus T circuits is also believed, but not known to be NP-hard. And in fact, it's been an open problem for a long time to prove that optimizing T-count is an NP-hard problem. And so we've proven that this is in fact NP-hard with a quite simple argument. So first, let's make this problem more concrete. Like, what is this T-count optimization problem that should be NP-hard? So we define the following way. So we are given a unitary Clifford plus T circuit, which implements a unitary U and an integer K. And then we need to determine whether there exists a potentially different unitary Clifford plus T circuit that also implements U, which uses at most K T gates. So this is essentially asking, can we find a version of the circuit which uses at most K T gates? So this is just the decision version. So we're giving an integer K, we need to determine whether there is one with at most K T gates. But using standard techniques for computer science, we can promote this to an optimization version where we do some binary search over the value of K, and in this way we find the optimal value of K. Although, even if we know this integer, it is then still not trivial to actually determine the circuit that implements this right thing with integer K. But this would be, like, to me, the natural way to encode this as a decision problem. Like, can we optimize T count? Okay, is that definition, does that make sense? Okay, cool. So the theorem of the first paper, the main theorem is that this decision problem T count is NP hard on the polynomial time Turing reductions. And the way we prove that is quite simple. We reduce from Boolean satisfiability. So determining whether a Boolean function is satisfiable is a very well-known NP complete problem. And so we show that if you can solve T count, you can solve Boolean satisfiability, and therefore must be NP hard. So how do we do that? Well, we have some Boolean function f, which is given in some poly-size description, for instance, as a tree of ands and ors, like some kind of normal form. And we need to determine whether there exists an x such that fx is 1, so whether f is satisfiable. So what do? So we use some standard techniques to build the classical oracle UF. So this is a quantum circuit that implements the following function. So it just puts the value of f of x onto a second qubit register. Yeah, and this can be implemented using standard techniques as some poly-size Clifford plus T quantum circuit. So essentially we need to use some ancillas, but this is besides the point. Like we just use some Toffoli gates and some CNOT gates, and we can encode any Boolean function in this way. Then, using this UF, we construct this circuit CF, which does the following. So we do a T dagger, and then we do this UF with the target on this bottom qubit. We do another T gate, and then you do another UF. So we can see that if we input some bit string X on the top wires, such that F is false, then this bottom qubit does not fire. It does not implement a NOT gate here. And then this T dagger and T gate, they cancel against each other, and we get an identity. And if it does fire, then this T sort of flips to a T dagger because it's surrounded by NOTs, and then they combine. And then you can check that the whole thing then is a diagonal circuit, and it implements the following. Now we're going to use this circuit to determine some properties of f. So in particular, we can check that if f is not satisfiable, so then f of x is always 0, so that means this is always 0. Well, then we see that this circuit always implements the identity. Then this phase term just disappears, and it's an identity. If f is always satisfiable, then f of x is always 1. And then we can simplify this expression, and we can do some rewriting, and we see we end up with this circuit here, where this is an S gate, which is Clifford. So up to a global phase, which we don't care about, this is a Clifford circuit. So in both cases, CF is Clifford, and that must mean its T count is 0, because there is a Clifford implementation of this same unitary, which means that, that T count 0 just means it's Clifford. Now suppose that none of these cases are the case, so that it's not always satisfiable, but it's also not always. It's not always satisfiable, but it's also satisfiable. So it's not satisfiable. So then we have a Z1 and Z2, such that f Z1 is 1 and f Z2 is 0. And then we can check that for these values, we get an I pi 4 for one of them, and we get just the same thing there itself. So we claim that then CF must be non-Clifford. And so the way we do that is that, well, we recall that a unitary U is Clifford, if and only if U dagger PU is Pauli for every Pauli P. And we just need to find a Pauli for which this is not true for the CF, if it has these properties. And so the Pauli we take is this string of x's. Sorry, I just need to disable a thing in the background, just annoying me. Right, sorry about that. So we take this string of Pauli x's, and then we can check that if we look at this conjugation of this Pauli on this particular state, Z10, we can just check what the action is. So CF on Z1, we know introduces a pi4 phase, so we get a pi4 phase. Then this X flips the Z1 to Z2. And then this CF here, it does nothing, so it just keeps Z2. So now it introduces a pi4 phase, but we know that Paulis can't introduce pi4 phases. So this conjugation can't be Pauli, and that means that CF can't be Clifford. If it's not Clifford, that must mean its T count is greater than 0. So the T count of CF is not 0. So now we by checking the T count of CF, we can determine some properties of F. So what can we do for this reduction? So we are given F and we construct the circuit CF. Then we use the T count oracle to determine whether the minimal T count of CF is greater than 0. If it is, then CF is non-Clifford, and hence F must be satisfiable. So then we are done. If it is not, well, then we know CF is Clifford, and we saw there's two possibilities for that. So then either F is not satisfiable, or it is everywhere satisfiable. So we just test one value. We just test like when we input all zeros. And then if this turns out to be not satisfiable, then we know it is not everywhere satisfiable, and hence it must not be satisfiable anywhere. Otherwise, if this gives 1, then we have a satisfying solution, and then we're also done. So with a single call to the T count oracle, we can determine whether F is satisfiable or not. So we've proven the following. Okay. So that's a kind of lower bound. We know that T count is at least NP hard. Then we can also determine an upper bound. And for that, we need the following complexity class. So this is NQP. This is non-deterministic quantum polynomial time. This essentially is asking, we have a quantum Turing machine, and we are asking whether there is a path that accepts with non-zero probability. So this is quite general. And this has the following complete problem, which is determining if two quantum circuits are exactly equal. So you might be familiar with the complexity class QMA, and this has a complete problem of determining whether two quantum circuits are mostly equal, but this is asking exact equality. And so what we can show is that T count is in NP with an oracle for NQP. And the proof is also quite simple. So we need to solve T count by using something in here. So we are given some poly-sized Clifford-Prestige circuit C and a number K. And we need to decide, is there a circuit C prime which has T count smaller than K, which implements the same unitary? So using NP, sorry, a bit of a cough. So using this NP class, we can non-deterministically choose a C prime, which is T count smaller than K. And this only works because there aren't too many of them. And then we can use NQP, the oracle, to determine whether C prime is actually equal to C because of this complete problem. And then if any branch accepts, we can return true. Sorry, I'm just gonna go for a bit. Sorry about that. Okay, so that's a upper bound to this problem. And in fact, this is very similar to a classical problem. So Boolean circuit minimalization. So this is given a Boolean circuit, find a minimal version of this Boolean circuit. This is a complete problem for NP to the NP. So here we are replacing a classical circuit by quantum circuit. And so we are replacing NP by NQP, because NP is needed to determine whether two Boolean circuits are implementing the same function. Okay, so this is just the hardness of T count, but we can actually reuse this argument to prove other hardness results. So for instance, we can also determine that Toffoli count is a hard problem. So here we are given a unitary circuit of NOT gates, C0 gates, and Toffoli gates, which implements some classical unitary U and an integer K. And now we need to decide whether there exists a unitary circuit over this gate set, which implements U, uses at most K Toffoli gates. And this is again NP hard. And the proof is quite analogous to the previous one. We just slightly changed the circuit we're working with. So we're changing CF to the following circuit. And here we can also check that if F is always satisfiable or never satisfiable, that this is a Clifford circuit, and otherwise it is never a Clifford circuit. And that is enough information for us to make the reduction. Very recently, I managed to actually prove a more general statement. So this works for any non-Clifford gate. So we fix some non-Clifford gate G and some error-bound epsilon. And then we define the following problem of G count epsilon, where we are given a Clifford plus G circuit. So G could be a T gate or a square root of T gate or a Toffoli gate or anything else, and integer K. And now we need to determine whether there exists a Clifford plus G circuit C prime, which again uses at most KG gates, such that it's not exactly equal to the circuit C. It is just within epsilon of the target circuit in the operator norm, where this alpha is a global phase. So we are saying if there is a global phase such that these things are close together. And then using a slightly more complicated argument, you can show that if this epsilon is small enough, like if it's smaller than about 20%, then G count epsilon is also NP hard on the polynomial time Turing reductions. So this is sort of entirely generic. It works for any non-Clifford gate. So if I give you any gate set which includes all the Cliffords, then optimizing the non-Clifford stuff is going to be hard. That's essentially the idea. And in fact, so this works for G count, but this also works for depth. This is entirely the same argument. It also works if you have multiple types of non-Clifford gates and you have some complicated metric that depends on, like, some gates are cheaper than others. Like, as long as all the Clifford gates are free and all the non-Clifford gates are not free, then this problem will remain NP hard. Okay, so that's the first part on the first paper, which sort of leads into the second paper. But maybe if there are questions about the first part, this should be a good time to ask them.
I have a question about this bound, and I wonder, do you have any intuition for the sine pi over 16, or what is intuition behind deriving this bound?
It just follows from the proof. Like if you, it has to do with, you have to show that if CF is not Clifford, that any Clifford approximation of it should be sufficiently far away from it. And this is just an easy bound to find, that like any Clifford will be at least this distance away. So as long as your epsilon is smaller than that, there will not be a Clifford approximation of this non-Clifford circuit.
Leah have a question in the chat. Oh, for the recording purposes, maybe I should just read it. So we could. So
the
Leah
norm,
said,
that's, yeah.
I
So the
missed.
norm for the G count circuit distance.
Mhm.
So this is the operator norm. So that's, well, these are finite dimensional matrices. So it is, you can calculate it in finite time. Yeah, it's essentially it's the supremum over the differences on arbitrary normalized input vectors. Okay, should I continue?
Sorry, one more question. Can you tell a little bit about upper bound for this problem G count epsilon? Is it also going to be NP to NQP?
I haven't thought about that. So let's go back to the arguments. So now we are given a polysize circuit C, and we need to determine whether there is a circuit C prime with T count smaller than K, which not implements the same unitary, but a unitary that's close enough. So now we are not determining whether two circuits are equal, we are determining whether two circuits are close. So I would guess that you could do that with a QMA oracle. So
Okay.
so it might be an NP to the QMA, but I'm not sure.
Can we ensure that the number of polynomials you need to check is still small in this case?
Sorry, the number of what to check?
Number of circuits that you need to check, that their number must be small in the sense that their size must be polynomial in the size of the input, right?
Yeah, so we have like a bound on the G count, and there is a limited number of Cliffords. So there is a exponential number of circuits over Clifford plus G that has like it's exponential in K. So I think that's why you can still do this with the NP oracle.
Okay.
Yeah, there might be details I'm missing, but I think this should still work. Although it probably won't be an NQP oracle because now you're checking.
Mm-hmm.
You need an oracle that can determine whether two circuits are approximately equal.
Okay, thanks.
Sorry, can I ask another question about the epsilon?
Mm-hmm.
So I wonder if you have a non-Clifford gate that lives in a higher order of Clifford hierarchy, for example, like a cyclotomic gate, do you get a smaller epsilon? Like, do you know how epsilon would change with respect to the choice of the G gate?
Yeah. For circuits that can exactly implement Clifford plus T circuits, even this problem with epsilon is equal to 0 are still hard because you can use exactly the same method as before. Because we can just reuse CF, and we only care about whether it's Clifford or non-Clifford. So it doesn't matter like how you implement the circuit, as long as you can exactly implement it. So for any cyclotomic gate, the exact optimization algorithm is also hard. Okay. So then let's move on to parametrized circuits, which was the original idea what I want to talk about. But yeah, I promise all this stuff is relevant. So parametrized circuits. So a parametrized circuits, the way I define it is we have gates from some discrete set, like Clifford plus T. And then we have parameterized phase gates, where there are like Z phase gates, which there is some function of some parametric phase that determines what the phase gate is going to be implemented in this thing. More formally, I can define a parameterized circuit as a map that goes from a parameter space into a unitary space. So for any set of parameters, values of parameters, I get a different unitary. This is just a way to say I have a family of unitaries that's implementable by a single parameterized circuit. Now we need to, I want to talk about optimization of parameterized circuits. So we need to define what does it even mean for parameterized circuits to be equal to each other. And the way we define this is by saying that parameterized circuits can reduce to each other. So I say that a parameterized circuit C1, which has some parameter space Rk, reduces to C2, which has parameter space Rl. When I can find a parameter map, which maps the first parameter space into the second parameter space, such that we have the following equality. So this C1 of a certain parameter is equal to C2 of this mapped parameters. And then we have this function, which is a global phase. So this is just saying we don't care about global phases in these circuits because they should still be equal. So we have a separate function, lambda, which is a global phase, but this phase can depend on the specific parameters in your circuit. So I think this is a reasonable definition of what it would mean for two parameter circuits to be equal. Although, like for equality, you could also ask that C1 should reduce to C2, but C2 should also reduce to C1, right? Because otherwise C2 might be more expressive than C1, for instance. Or the other way around. Okay, so now we can define the problem of parameter count. So here we are given a parameterized quantum circuit C, which has parameter space Rk and an integer L. And we need to determine, does C reduce to a circuit C prime, which has parameter space RL? So this means we have K parameters. Can I reduce this to a circuit at most L parameters? So that for me is the natural equivalent of this T count problem, but now parameter count problem. And again, parameter count is in fact NP hard if the discrete gate set includes Clifford plus T. And this is easy to see because we can use pretty much the same argument as before, but now we replace CF with the following thing. And then we can again check that if F is not satisfiable, always satisfiable, these parameters can fuse together. And then we can just check the parameter count of the circuit. And if it's 1 or 2, that determines properties of F. And that allows us to solve Boolean satisfiability. So parameter count is again NP hard. But yeah, this seems quite obvious because here we are sort of have these obstructions with T gates and stuff. So that raises a question of, is this parameter count problem still hard if we only have Clifford gates? And the answer to that is also yes, but this is quite in a cheap way. And that's because if we have some gate Z alpha and a gate Z phi alpha, where I define phi alpha as this function, which is a very reasonable function, it's linear, it's an affine function, it's very simple. Then obviously, if I put these gates into a row, they combine together into a T gate. So if I allow sort of arbitrary functions phi on my parameters, I can still make T gates. And so then this problem will still be NP hard because I can reduce it in the previous argument. But this, again, this feels a bit cheap. This feels like cheating because you're sort of inserting these T gates in like a very cheap way. So let's try to get rid of that. And let's define a more restricted class of circuits. So I define a parameterized Clifford circuit, which consists of Clifford gates and parameterized phase gates Z alpha. So now I no longer allow an arbitrary function that's alpha. I can only just put in this alpha directly from my parameter space. So we can still use alpha multiple times. So I can use it at multiple spots in my circuit. But sort of this function that determines what the phase in my diagram is going to be always the identity. Now, we conjecture that this problem is still hard for parameterized Clifford circuits, although we've not been able to prove it. But we do have some evidence, and this is courtesy of Thomas Lakonen, who came up with this. So we do know this is the case for post-selected circuits. So parameter counts for parameterized Clifford circuits that are post-selected, that is, in fact, a hard problem. And the way we see that is we can construct post-selected parameterized Clifford circuits, T alpha, which, not T alpha, but like this is like Toffoli alpha, like I call it T alpha, because this implements the following unitary. So this implements a Toffoli gate, but with this non-normalized scalar factor in front. And this is going to be our first ZX diagram, or in fact, our first ZH diagram. So this is what this thing looks like. So this Toffoli construction with like an alpha by 4. So this implements a Toffoli gate with this scalar factor. And we can check that it's actually proportional to the following diagram, which is the following post-selected circuit. So here we have some ancillas, and here we have some post-selections. And then here we have a controlled alpha phase gate and another controlled alpha phase gate. Yeah, so we can check that we can decompose such a controlled phase gate into just C naught gates and Z alpha gates. So this is in fact a parameterized Clifford circuit with post selections. And so since we can implement Toffoli gates, and we know that optimization involving Toffoli gates is hard, that means we still get a hard problem. And you might think like, well, obviously there's post-selected circuits, like, and we know post-selected circuits, they can do much more than normal circuits. So of course, this is going to be a hard problem. Like it doesn't give you any evidence for regular circuits. But the proof I'm going to show you of a restricted problem, which is efficiently solvable, also solves the same problem efficiently for post-selected circuits. So this is why we think this evidence is good. It's because, doing the same restriction for parameterized circuits and post-selected parameterized circuits does give you an easy problem, while here it is still hard. Okay. So what now? But I'm trying to find a subset of this problem of parameterized of parameter count, which is easy to solve. So we now know we need to restrict our discrete gate sets to Cliffords, and we must allow each parameter to only occur once. Because if the parameters occur multiple times, we can do this trick, at least in the post-selected setting, where we have where we can implement the Toffoli gate. So conjecture: if we don't restrict which reductions we allow, this problem will still be hard. And again, we haven't proven this, but we have some slight evidence for this. And this evidence, for instance, is that if we consider, for instance, the generalized Euler decompositions, so here we have a Z rotation, X rotation, Z rotation. We know this is equal to an X rotation, Z rotation, X rotation, where these parameters alpha and alpha prime, they depend on each other in some very complicated manner. So you could imagine reducing some parameter circuit to a different parameter circuit with fewer parameters by sort of stacking these Euler decompositions or decompositions on top of each other. But it feels like, because these functions are so complicated, that this should result in a hard problem, but we've not been able to really prove it. So one thing that happens in these complicated reductions is that the parameter function that relates these alpha to the alpha prime, this is in fact a discontinuous function. And a very reasonable assumption to make, I think, is that this parameter function should be continuous. For instance, for variational circuits, we often care about them in the context of machine learning. And there we want our function of parameters to be continuous or to be smooth. So a reasonable assumption to make would be that our reduction function f should be a smooth function. Now, in fact, if you go one step further and we say if f is an analytic map, so this means it's like an infinite polynomial function, then what we can show, because again it's a phase function, so it should sort of exist on the unit circle because it's also periodic. Then we can show that in fact f of alpha is just an affine function. So we just have some matrix, and in fact this matrix is a matrix of integers, and this again has to do with the fact that it must be periodic, and has some constants. So even though we could have in principle some very complicated maps, if we say they need to be analytic, then the restrictions on periodicity force it to be some very simple affine map. And that finally gets us to the definition that I want to work with, which is that we have a parameterized Clifford circuit C1, and we say it affinely reduces to C2, where for all alpha we have this relation now. And actually there should be a global phase here, but I sort of ignored it. So they are related by just some matrix. Now, one thing to notice is that if we have a parameter alpha j on the left side, then this m, it can copy the single parameter to multiple spots in C2 if the jth column of m is non-zero. So even though we could have unique parameters on the left-hand side, these parameters could be non-unique on the right-hand side. So this breaks the condition of sort of use once parameters. It's sort of you're cloning the parameters to multiple spots. So for now, we're going to make the assumption that this matrix M, or this reduction, is what we call parsimonious, meaning that it has at most one non-zero element in each column. So this greatly restricts the types of reductions you can make. Okay, so now we have this following problem, which I call affine unique parameter count. So we are given a parameterized Clifford circuit C with parameter space Rk, where each parameter is used at most once. So the sort of unique parameters, and the integer L. And we need to decide whether there exists a parsimonious affine reduction to a Clifford circuit C prime with parameter space RL. So again, affine reduction meaning related by some matrix, and parsimonious meaning it has no cloning on the parameters. Maybe I want to say a little bit more about this condition of using a parameter at most once. So if you use a parameter multiple times, I can always make a more general circuit where I just redefine, like I just introduce a new parameter at that spot, right? Like if I use the parameter alpha in 2 spots, I can just say, well, in the second spot, I'm going to call this new parameter beta, and this is going to be a more general circuit, right? So you can always make a reduction from a circuit that uses a parameter multiple times to a circuit that uses each parameter uniquely. So this assumption on having unique parameters, you can view this as saying, I have no information on my parameters. I don't even know if this parameter at that spot is equal to this parameter on this spot. So this is like the most black box setting you can imagine. Okay, and what we prove is that affine unique parameter count can be efficiently and constructively solved. And in fact, an existing algorithm based on ZX diagrams does this. So our previous result, graph theoretic simplification of ZX diagrams, together with sort of phase gadget fusion. If you do that algorithm, that in fact gives you the optimal parameter count for this problem. So this affine unique parameter count can be efficiently solved. Okay, so how does that algorithm sort of work? So let me give a very high level description of this. So what we do is we take our Clifford plus parameter circuit and we write it as a ZX diagram. This is very straightforward. Then we rewrite it to a graph-like diagram. So a graph-like diagram is a diagram which only has Z spiders and all the spiders are maximally fused and you only have Hadamard edges between 2 spiders. So this is a form of ZX diagrams that is used often when you're doing optimization because it's more amenable to automated rewriting. Then we apply sort of a suite of operations that remove spiders from our diagram. So these are local complementation, pivoting, and boundary pivoting, and phase gadget pivoting. So these are variations on the pivots. And what this does, what this accomplishes, is it removes all the internal Clifford spiders from the diagram. So now every internal spider, so a spider that is not connected to an input or output, will have a parameter as its phase, or it will be part of a phase gadget where the phase gadget will have its parameter as a phase. Now, what we do is we fuse all the phase gadgets that can be fused. So this means if 2 phase gadgets have the same neighborhood, we fuse them together. And this adds the 2 parameters together. And then we extract a circuit from the diagram. And this can be done because the diagram has G-flow. So then we know how to efficiently extract an ancilla-free circuit from this diagram. And so the claim is that if you do this, this circuit has optimal parameter count, where optimal is defined with respect to this problem I defined before with like the unique parameters and parsimonious affine reductions. Yeah, so then in other words, the only thing that removes superfluous parameters from your diagram is phase gadget fusion. Because the only step here that can actually remove a parameter is this step. So we fuse phase gadgets. I'm treating sort of identity removal and the fusion of phase gadgets, of phase that happens then as like a special case of phase gadget fusion. But yeah, this is the only rewrite that removes parameters. Okay, so how do we prove this is optimal? So the proof is a bit technical, so you can check out the paper if you want the details for that, but this is just a high-level overview. So we are assuming that we have a diagram D1, which is given to us as a result of applying this algorithm. And we are supposing it is equal to some D2 with some parsimonious affine reduction. Now, first we show that the entries of M can only be plus or minus 1 or 0. So they cannot be 2 or 3. And this has to do with, you can check that if we have an alpha on one side and like a 2 alpha or 3 alpha on the other side, then the only way this can be true is if alpha doesn't actually change anything in the diagram, if it only influences the scalar factor, and this cannot happen in a quantum circuit. Then we use this simplification on M and also on lambda. So we also show that lambda needs to be simple. That in fact, all this information about the reduction can be captured in some simple diagram P. So P is encoding the entire reduction, And P will be some simple diagram of some spiders. So it will just be some Z spiders and some X spiders that encode which phases get fused and which phases get negated. So if there's a -1 in this matrix, that means the phase gets negated. And that means there's an X spider on this thing here, which sort of encodes this phase negated. And that's all put in this diagram P. So now this D2P is actually some Clifford diagram. And that allows us to study this diagram using stabilizer theory. And what we can show is that this diagram D1, if it resulted from the ZX simplification strategy, its underlying graph state must not have certain stabilizers. Because if it were to have those stabilizers, then we could have fused more parameters. And using that, we can argue that P can't contain additional fusions. So it can't be that P sort of allows you to fuse additional spiders. And then we can conclude that any reduction to D2 can't contain fewer parameters than D1 already has, because P is not fusing anything additionally. And so that is showing that like this algorithm is in fact optimal. Okay, so we proved this using a ZX perspective. But in fact, we can try to relate this to a circuit rewriting strategy. So the ZX strategy we used in this paper by Will Simmons, relating measurement patterns to circuits via Pauli flow, he shows that this ZX strategy that we use, that's described in this paper, is actually equivalent to the rewrite strategy described in this paper. So what they do here is they take a Clifford-Pastis circuit, and then they write the circuit as a combination, as a series of Pauli exponentials, followed by a Clifford circuit. And then what you can do is you can just try to merge Pauli exponentials when they are the same Pauli exponential. And so there, the only optimizations come from merging Pauli exponentials. So this suggests that if you write your circuit as a series of Pauli exponentials, followed by some Clifford circuit, and then you just fuse exponentials of the same Pauli whenever you can. So whenever you can commute them past Pauli exponentials that they commute with, that this will merge your parameters. And this suggests that this in a black box setting is the only thing you can do. So this is the optimal circuit rewriting strategy if all you care about is merging parameters of a parametrized circuit. Again, assuming these conditions on your reductions and on your parameters. Okay, so here we had to make this assumption that the reduction was parsimonious, so that it didn't copy parameters to multiple spots. But this is quite a strong assumption. And in fact, we think this assumption is not necessary, although we've not been able to prove it. But we have been able to prove special cases of it. Yeah, so our proof of optimality, it only works when this affine reduction M is in fact parsimonious, meaning it has at most one non-zero element in each column. So what about the general case, if like M is arbitrary? So what we know is that if we have such a reduction, where every column of M contains at most 3 non-zero elements, then there exists a different reduction, M prime, which is parsimonious. So that means it has at most 1 non-zero element in each column, such that D1 is equal to D2 with this parsimonious reduction. So that means that if we have at most 3 copies of each parameter, we can reduce it to a different reduction where we only use it once. So this is saying that if I have a non-parsimonious reduction, every copy of alpha happens in that kind of trivial way where I can combine them together anyway. Now I expect that this should also hold when you increase the amount of elements allowed in each column. But the proof we use to go up to 3 elements doesn't generalize. So that's kind of a problem. And this proof is already quite complicated. So that's, yeah, it would be a nice project for someone to work on. But we tried very hard and we couldn't make it work. Yeah, so we expect that it should hold for any M, but we don't know. Okay, so to conclude. So we've seen that optimizing the T count of a Clifford-Pastis circuit is NP hard. Also, the Toffoli count of classically reversible circuits is NP-hard. We've also seen that approximate G count optimization for any non-Clifford G is also NP-hard if the approximation factor is small enough. And yeah, we also know that optimizing the parameter count of parameterized circuits is NP-hard in general. Even if you restrict your discrete gates to Clifford, and probably even when you only allow Z alpha instead of arbitrary functions of the alpha. But we do know it is efficient when the parameters occur on unique gates and when we don't allow this parameter to be copied in the reduction. And then the optimal strategy is just to fuse Pauli exponentials when you can, or in the ZX version, it is fusing phase gadgets when you can. So in a slogan, you can say that for black box phases, so if I just know it's not Clifford, but I don't know anything else, then fusing gadget is the only thing you can do. That's the only thing you can do to combine these phases together and nothing else. Okay, so that's it. This was based on these two papers, so you can check them out if you want. And yeah, thank you for your attention.
Thank you. So let's give John applause with emoji or whatever way that you prefer. And now, oh, okay, so Leah, I have a question. Why exactly is it 3 copies, the intuition for the proof?
So what you can do is so what we have on the what we have on the left-hand side is a Clifford diagram with some unique phases put into there. And on the right-hand side, we also have a Clifford diagram, but now there's multiple copies of the same phase put into there. Now, this is very weird. Like in general, this is not possible. And so what you can do is you can already derive some quite strong conclusions from this on like properties that the graph state should satisfy. You can show that like certain states, if you input them, they should be sent to 0 by this Clifford state. Now, what you can do is, since a Clifford state can be written as an affine with phases normal form, so this will be, it is a superposition over some affine subset of all the computational basis states together with some phase function. Since we know that the affine, this Clifford state must be 0 on certain inputs, we can derive consequences for which affine functions are allowed, which affine subspaces are allowed. And if the number of copies is small, we can sort of manually investigate this and rule out all possible cases. And we can sort of check that like in each case, we can just combine the phases together and we get a trivial, we get a parsimonious reduction. But if the number of terms becomes larger, this analysis fails and you need new assumptions. So you need new arguments to do this. And we just haven't been able to come up with any.
So I have a question about the uniqueness of the phases. And just now you were saying you do not allow the repetition of the phases. And when you said if there exist repeatedly appearing phases, then you can let the first one being alpha, the second one being beta, but I didn't follow the reasoning that part. Could you elaborate a bit more? Like when there are repeated phases, what would happen?
Okay, so a common scenario where you want repeated phases is if I want to implement a controlled phase gate, then the decomposition into phase gadgets. For instance, if I want to have a controlled alpha phase gate, then the way I would do it is I would do a alpha over 2 gate on the top qubit, or do an alpha over 2 gate on the bottom qubit, and I would do a 2-qubit phase gadgets with a minus alpha over 2 phase in the middle. So this implements a controlled phase gate. And this requires 3 copies of alpha. So if I have a variational quantum circuit where I have a controlled phase gate, then I would have copies of the same parameter occurring if I decompose it in this way. But if I have such a circuit, I can make a more general circuit by instead replacing these three alphas by alpha, beta, gamma. And this can still encode my controlled phase gate, but now it can also encode more things, right? So in this sense, this controlled phase gate circuit reduces to a more general circuit, which has three parameters. And in this circuit, there's only unique parameters. Yeah, so the uniqueness on parameters, this is kind of because like our proof is really about there is no special structure on black box phases, which is that you can only combine them in trivial ways. And if you know that certain phases are equal, then you do have some information on these black box phases, and they're not truly black box phases anymore because they have some relations between each other. And this allows you to do more complicated things. So for instance, in the paper, we show an identity. So this actually, I can explain this. If I have a controlled Z alpha phase gate, and I have an anti-controlled X beta phase gate, so anti-controlled means it fires on the 0 state instead of on the 1 state, then these two gates commute because one of them fires on the 0 state, one of them fires on the 1 state, so they never fire together. So I can just commute them to each other, through each other. But if I expand this controlled Z gate and this controlled X gate into sort of atomic phases, this identity in ZX looks very non-trivial. And in fact, this is in the completeness result by the people from Nancy. They had to assume this as an axiom to prove such identities. And so this is like a non-trivial identity that you get between circuits that have repeated phase gates. And so optimization of circuits that have repeated phase gates becomes much more complicated because you have to, for instance, reason using these kinds of identities that you don't have in the case where you have unique phases. Oh yeah, so one result I didn't mention, which I really should because it's a select seminar. We have a completeness result. So if you have a Clifford diagram with black box phases in it, where each phase occurs uniquely, and you have two such diagrams that are equal for every value of the alpha you can put in, then you can prove they're equal using the Clifford ZX rewrite rules. So Clifford ZX rewrite rules are complete for parameterized diagrams where each parameter occurs uniquely. And this also holds even if the diagrams are only equal up to global phase, but then you have to be a bit careful about what it means to have completeness for diagrams that are equal up to global phase. So Ariane asks, what if you know the circuit has some structure? Like in quantum kernels, you might use U of X params and a U dagger of X prime params. Yeah, so if you have any structure, this result doesn't work because probably you will have more non-trivial identities.
So the reason that we have NP hard is because we are missing some of the ZX diagram rewrite identities, so we're not able to efficiently verify whether one diagram is equal to the other.
It's not about missing identities because we have a complete calculus. It's that it's hard to find the optimal configuration of them because there are, in a sense, too many identities. Or it's not clear in which order to apply the identities.
I have another question. So I'll let other people to think. I wonder if we can prove the hardness of optimizing T count for cubic case. How hard would it be to generalize it to high dimensional quantum circuit?
Ah, interesting. I think the argument we give should work for any qubit. Like as long as you can make a if you can make an equivalent of this circuit. So the crucial part is we have some circuit which you can exactly represent in the gate set you want, namely this UF or the CF, which is Clifford if F is not satisfiable or always satisfiable, and is non-Clifford for any other choice. Like as long as you can make a circuit like that, the argument continues to hold. So this should also work for qubits. In any case, it would be very surprising if this problem is hard for qubits, but easy for qubits. That would be super surprising.
And Corbinian has a question in the chat. So it's still on the first paper. What about the complexity of determining optimal gate count of any Clifford gate in a Clifford plus T circuit? Do you think it is something like determining the optimal count of any non-Clifford gate is NP hard? Determining optimal count of any Clifford gate is efficient.
I think any is not going to work, but I wonder if we could adapt this argument and say, because we know that if F is not satisfiable, its identity, and if it's always satisfiable, it is just an S gate. So in that case, the C naught count is 0. And if it's not satisfiable, then you can probably prove it requires at least one C naught gate. So then if you ask for the optimal C naught count of this circuit, that should also be able to prove that that's NP hard. So that's actually something I should work out because that's actually very relevant. Although, isn't it already known that determining optimal C naught count is NP hard because of like relationship to Gaussian elimination and stuff?
I'm not sure that's where I was asking, but if it's indeed the case that already optimizing CMOS is NP hard, then of course this doesn't hold.
So what's the question? Like, is it that you're picking a Clifford gate and you want to optimize the amount of that gate, or is it more complicated than that?
Yeah, no, I was just wondering whether if we just replace those two T gates here with Clifford gates, can we say like we can determine an optimal Clifford gate count efficiently or not? But yeah, maybe that's not the case. I see that. Yeah.
Yeah, so like here in this case, we do get so identity or just a single gate. So maybe we can ask if you can prove in every other case CF will require at least 2 Clifford gates, which seems reasonable. Then you can ask, is the Clifford count of this circuit 1 or less? And if so, then we know that one of these things is the case. And if it's bigger than 1, then we know it is satisfiable. So then that would show that optimizing Clifford count in a Clifford plus T circuit is also NP hard.
So Leah has another question. So at the start of your talk, the 3 equivalent problems, how does T count map?
Not exactly in a clean manner. So T count is about arbitrary Clifford plus T circuits. And this is about the T0 count in C0 plus T circuits. So this is without the Hadamard gate. Actually, I think it's a bit of an open question whether there are non-trivial identities that reduce T count that involve the Hadamard, because all techniques I know, they try to move the Hadamard gate out of the way. Like, I don't know if there's sort of, yeah. Actually, there might be one in this paper by Harney and Bob, this like 2-qubit gate identity. I think actually that's a Peter Salinger identity, actually. Yeah, like there's no clear relation. It's like one does not imply the other does not imply the one. So that it's not like you can conclude NP hardness of these problems from what we've proven or the other way around.